this will be the third year. The first year we did it, it sort of asked, well, what are your fears and concerns about going to extreme scale? Maybe at the time we were thinking of, oh, I don't know, 100,000 cores. Let's pick that as a number. So 3 years ago or 2 years ago, when you were thinking of 100,000 cores, what problems were you really concerned about, and did those problems turn out to be as bad today? Or did things that you thought weren't a problem become a problem?
I'll start. So we brought, Chombo has a kind of a flat MPI, parceling out boxes to processors. And my main concern with going up to 100,000 processors was you need load balancing. So at a 1% load imbalance, technically you shouldn't be able to strong scale more than by a factor of 100. So I was concerned that I really wouldn't have problems where I could weak scale. I know my code weak scales out, and I could prove that I could do my solves out at 100,000 cores. I could do my explicit schemes at 100,000 cores, and my I/O would hold up. So that was all ended up being true. So I didn't end up having problems doing that. So now I'm confident that at 100,000 MPI ranks, my code will work pretty good. But I don't think I can go to a factor of 100 more than that. So I think I have to stop here. So I think I have to stop at about 100,000 because that's as much as load balancing as I can tolerate and regridding as I can tolerate. And the networks aren't getting dramatically better. My next generation of network is maybe only an incremental improvement over what I have. So my latencies will be bad. Those things will be what are going to kill me. So my main fears did not manifest. And I'd say 3 years ago, they were starting to give me GPUs, and I said, I'm not going to do that. And so I haven't. So I've watched other people get Big Insight awards, and I've had to sit on the sidelines because unless I get Myra time or Edison time, I couldn't really use Titan time effectively.
Answer is in two aspects. In terms of unstructured mesh solver technology, our biggest concern on going to 100,000 cores did not have to do with the current solver that we were working with, this software called Pasta, and solving things like Navier-Stokes equations on anisotropic unstructured grids. We actually weren't concerned about that. Where our concerns were on going to 100,000 cores, and we're now at basically 750,000 cores and 3.1 million ranks, was much more in terms of when do we start doing harder problems, harder from the standpoint of problems with numerical ill conditioning issues and dealing with those. The work that was done jointly with University of Colorado, well now University of Colorado and University of Colorado, really addressed that quite well, and that now we can get to those points quite nicely with PETSI. And the bottleneck, we were never worried about the bottleneck of the finite elements, straight finite element side, or the solver side. It's always the assembly and or preconditioning aspects where the two meet together that's a problem. So it's, if you will, it's that bridging, and there's been some very good work done there, although we're still going to have some issues if we start doing many adaptive steps. So the second part of my answer, and I'll try to do it fairly quick, is the whole issue of executing entire workflows on the massively parallel computer. As I mentioned yesterday, we take a particular perspective of, I'm going to go as far as I can, but whatever I use will be methods that can be fully automated. I can start from a CAD model and do everything on the massively parallel computer. And that means you use very specific technologies that are harder to scale. Those workflow steps and the gaps between them continue to be the hard parts, and my 2 minutes is up.
So I think one of the concerns that we have all along is just kind of cleaning up cobwebs that lie around within the software stack. So there's bits of code that were written, back in the age when a couple hundred processes was a lot, and they're not that scalable. It was just kind of something convenient to do at that time. A lot of it's not even a deep mathematical problem, and yet occasionally those become a bottleneck at larger scale. Often they're kind of straightforward to resolve. Other times it's something like Parmetis, which has a funny license, which is part of the problem. And the other part of the problem, it has a basically p-squared data structure. And so that falls over at some point. And so you can throw out that concept of partitioning, but then the quality goes down. So we don't have good solutions for that right now. That's, it's something that we need to get back within the software stack, something that does keep up with the other components. One of the other major factors, because we work on a library, we get called from many different contexts. The applications may assume different things about the environment. They may have a kind of non-scalable model. So for example, there's a lot of finite element packages out there that have this concept of like their global indices are kind of too important and they end up translating global to local. And that's not a high performance or not a scalable operation to do. So if they kind of restructure their philosophy, it would all be fine, but there's a bunch of legacy built on doing things in that way. And so those kind of assumptions within the application can end up being bottlenecks.
So a couple years ago, or I don't remember if it was a couple, even last year. Yeah, wow, 2 minutes is up. That's right. Thanks, Matt.
Yeah.
The question was whether or not we had concerns, and I think at my answer then was the same as now. I actually enjoy, the extra order of magnitude of cores we have to deal with as they come along, because it leads to lots of interesting and fun new research, both on the computer science side as well as on the mathematics side. So for me, it's not been so much of a concern. Obviously, there are lots of technical issues to deal with, but I feel like we've always had technical issues to deal with every new generation of computing platform. Maybe if I had a concern with the whole exascale thing that's going on right now, is that I felt like maybe we were worrying a little too much, and it might actually cause many of us to work on things that were more of a sidetrack and not necessarily productive. So if I had a worry, I'd say that was the closest thing to it. But
Okay, questions from you all? Yes?
My problem with running as many processors as I can is that we have a small cluster and I have to sit in the queue for hours and hours if I want to run as many processors as I can. So you guys have these giant computers. Is there money out there to make those bigger and available to a government agency like the EPA? And what to do about this not having enough resources to run on?
Well, so we have the opposite problem very frequently, say within DOE computing, where there's an incentive to run at larger scale than the application naturally can use. And so an application like climate, the production, the resolution that they want to run as their target for the next few years is not big enough to get in the capability queue at Argonne. And so they bundle together unrelated runs to make it look like it's much bigger than it is. They're independent runs, and they don't strong scale to be large enough to get in the capability queue, and the capability queue is necessary to get a longer wall clock limit and to get priority. And so it's this ridiculous game.
Time to solution matters.
Yeah.
And so we do accept ensemble jobs as appropriate for the big machines if it's a time to solution issue. If you can do it in 2 months instead of 20 years, it makes a difference, even though it is an ensemble of many different jobs.
Yeah, so a fair queuing policy would be better for everybody.
And as far as access to the big systems, although it's not guaranteed year after year, the leadership computing facilities are open to the world. It doesn't matter whether you get your funding from EPA or Deere Tractor Company. If you can put in a proposal that's worthy of it, but you're not guaranteed, of course, long-term access. The hope is that, at least my hope is that by you, for example, being able to demonstrate the value of running on big machines to EPA and Lockheed Martin, they will eventually get their own machine that's bigger and better suited for your jobs. Does that make sense?
Yeah, it's, the EPA is not gonna pay for, when you submit proposals to
You
run
get-
on your computers,
It's
do you
free.
get, it's free, it's free?
So long as you're willing to publish, it's free.
Okay.
People from all over the world can do that.
A specific suggestion. Now, I don't disagree at all. There are various ways to write proposals in that. Now, the question is being competitive on those proposals, and my specific suggestion to you would be to make contact based on some of the people you've met this week that have been up here lecturing. See if you can get one of those interested in working on your problem with you, and they'll very much be able to tell you how to get on the inside of being able to get some of these access, because there's actually a whole variety of different levels and possibilities. But, you know, speaking as a university person, you know, to be able to get those things, a lot of that does require having the right, developing some of the right contacts and working those. And frankly, you know, one of the best things you guys can get out of this meeting, because you're probably super saturated and there's no way all this stuff's sinking in at this point, is just remember the names of all the people who are up here and the things that they work on, and see if you can start making contact with some of those, because, you know, to varying degree of how many years, but some of us many years have been involved with this and know how some of these processes work.
Okay. Other questions?
I'm
sorry, Brian.
I'll just say that at NERSC, so this is at the National Energy Research Supercomputing Center at LBL, the time to submit proposals for next year's cycles is now open, so anyone can apply. You do not have to be DOE. You do not. So we have NIH, we have NSF people apply, and the success rate is about 35% of the people on that machine are not DOE people, don't even have a DOE partner or collaborator, and you can get a initial allocation fairly easily. You know, if you're in the, you know, there's a beginner allocation where they'll just give you 20,000 cycles just for showing up, just for filling out the application, just for saying I would like to run, and saying my code does compile with MPI or something. Bang, there's some cycles. Show us that you can run.
Follow-up question?
Can you email everyone the application?
I'll give you the link to the webpage. That's
On Friday of next week, I'll show some slides that have that information for the 3 facilities.
Okay.
Did I see a hand go up back there? Maybe halfway? Go ahead.
What are the challenges in getting good scalability for fully implicit algorithms? Like on exascale machines, I can imagine that explicit algorithms will scale well, and the algorithm is good, but I mean the machine, maybe we have some network problems that will prevent explicit algorithms from scaling well, but we have like inherent problems with implicit algorithms. So what can we do about that?
So challenges with scaling implicit and explicit algorithms. Okay. Jed?
Well, so first I would say explicit methods don't scale well because you need more time steps. So in terms of time from, to be able to reach a target accuracy, as you tighten that accuracy, so you need more resolution and you also need more time steps, that scaling doesn't work well. That really falls over because you need more time steps. Now, implicit methods potentially can step over that. For transient simulation, usually you're still following some slower time scale in the system. And so also you need more time steps. But it's possible that as you increase resolution, as you tighten your accuracy tolerances or you ask to solve more complicated problems, say on larger domains, it's possible that you see more multi-scale phenomena. And in that case, the implicit solves can get more challenging. Now, implicit solves on problems that we understand, if it's not getting somehow like more complicated, more multi-scale, then I think we're actually reasonably safe there. Our networks are becoming higher radix, our our multigrid solves actually scale pretty well. So for the problems we understand, that's fine. The thing is, as we ask for more accuracy, we have higher fidelity models. We have more multi-scale phenomena that shows up. So the problems actually become more complicated, and that's a mathematical issue, a convergence issue. And it's very interesting. It's something that we like to work on. But it's really not related to the ability of the computer to keep scaling on that kind of thing.
Other panelists want to go ahead? Ron?
So yeah, I agree with Jed on the time stepping part in particular. And there's actually a lot of research that is just blossoming all over the world now, looking at ways to solve in parallel in the time direction as well. So you do a full space-time parallel approach to things so that you can take advantage of the high levels of concurrency that we're getting in the future.
Go ahead.
From what people have been saying this week, and also what I've heard a lot in the past, people say that we're increasingly sort of bandwidth limited, and so therefore there's more scope to play with more computationally intensive algorithms than there might have been in the past. I know that Brian, you were saying before that for hyperbolic problems, you don't think that like higher order spectral elements or DG or whatever are a good idea. But I just wanted to hear what people thought were some potentially useful, sort of more computationally intensive algorithms that could be used in these more sort of like bandwidth limited machines. Algorithms that people have disregarded in the past because they're too expensive, but that now could be quite useful.
Well, so we can raise the order of accuracy, but raising the order of accuracy tends to only help if the problem is smooth enough. So if you have a problem, say a subsurface flow, you have lots of different rock types, and it's basically heterogeneous at every possible scale, then increasing the order of accuracy doesn't do you any good. So in fact, very low order of accuracy is good. Now there's methods like multi-scale finite element methods that try to do some initial coarsening. So they don't need to explicitly represent that finest scale. So there's some promise in things like that. I think one interesting direction to go is stop assembling matrices. So matrices are a lot of your kind of heavy data structures in terms of using a lot of memory. And so I've done some work in geodynamics on that, where we used to assemble matrices, and we're using like quadratic finite element methods, like Q2, P1 discontinuous. That element was chosen for stability reasons. It's necessary for stability and accuracy reasons for the problem, not because it's smooth. It's not smooth enough. You don't see the design order, but you need it for stability. And there, by going to a matrix-free approach, we got about a 3x end-to-end speed up. So that's by reducing the amount of memory that's used. Now, if you just boost the number of flops that you use and you still have the same amount of memory, it's probably going to run slower. A little bit slower. Not a lot slower, maybe, because the flops are cheap. But if you want something to actually run faster, you have to find lower memory representations for the data structures. I think that's an interesting direction.
A couple of comments on methodology. So I was going to mention the matrix-free types of techniques, the various element type level types of things. But often, and the other methodology, one that certainly receives a lot of attention, is discontinuous Galerkin methods, where they go high order on the individual elements, but you can do what you want between. So depending on where your heterogeneities are, if you just have to resolve a few shock structures, that's fine. In the example Jed said with the rocks and that, well, that's probably not going to be very helpful there. But in other cases, it works well. But realize with those methods, you are going to have a lot more degrees of freedom, because you basically, instead of having things shared, they're on two sides, and then you got to communicate between them, and you have to account for the physics of that. So you can trade flops and that. The other comment I was going to make is my observation on the communication avoiding algorithms I've seen to this point. Avoid communication by using more memory. And they tell us both are bad. So back to the last comment that Jed was making. How do we deal with knocking down both of the things, and that's a hard problem.
So I'll reiterate, the best algorithms that people write in Chombo are matrix-free. Our matrix-free runs are probably the only ones that actually get kind of 1 advance per second. Once I build the matrix and start having moved the matrix back and forth, I drop back to tens of seconds to get an advance. So that data structure and the data movement and everything involved with that data definitely slows the code down. And I don't think it's going to get better with the machines as they go. I think it's going to get worse. So yes, matrix-free is a very good idea, and I'm looking to get us back on that horse. It was always our philosophy originally, and we just kind of got knocked off because the physics came at us too fast. Going to higher order is an important part. So our fourth order multi-grid solver gets the same accuracy for 1/100th the memory. So to a given tolerance, my fourth order can get it on a coarser grid to the same fidelity. I think that's going to be true in space and time. I think you need to have high space and time accuracy. I think just plain old higher accuracy, not necessarily DG getting there, but I think the issue with DG has things to do with what the accuracy really is doing for you. I think the extra degrees of freedom aren't being very used efficiently. But if I take a uniform grid and I do a high order stencil, I'm still moving in, that grid comes in, that grid goes out, right? And if I do higher order, I just need to reach more of that local storage, but I'm actually, if you actually look at the kind of bytes that must move and flops that you have to do, if you organize the calculation well, you can still get more fidelity out of that same AMR hierarchy. So I think that's the direction we're going in. So I have research projects doing that kind of work. So I'm looking at high order pick methods, high order elliptic solvers, high order explicit schemes, high order IMEX techniques. And I think that's how I'm going to get my next push, because it maps better to the kind of parallelism they're giving me. They're giving me more vector units, they're giving me more parallel ops. So I think that's the way I'm going to get there. And I'm running into other limits, right? Very high order schemes, you can run out of registers. Very high order schemes, you can run out of reorder buffer. You can run out of other things become the thing your head bumps up against in terms of performance. But at least then I'm in a different regime, right? I know how to move in a different direction. I know how to get registers back. So it's an interesting place to work in. I think I definitely recommend second order schemes have to get set aside when you can. Fourth order may be the limit because, right, every time you hit a discontinuity, you drop to first order, right? You can't really beat Godunov's theorem.
Go ahead, Ron.
So related to your question, I just wanted to make a comment. A lot of times we look at the architectures that are about to be delivered or have been delivered, and we ask ourselves, how can we best utilize this? And computational intensity is one of these things we talk about a lot right now. But ultimately, you have to remember that you're solving a physics problem, and you want to solve that problem as quickly as you can and use as little power as you can. The best algorithm, the one that will do that best, may not have high computational intensity. Other issues like, reducing communication is important, but if it's a physics problem and it's coupled, you have to communicate. You can't just not do it. And so looking at algorithms, you have to be careful when you're designing new algorithms to achieve some of these goals that are good for the architecture, and remember that they might slow down the overall solution time, either make the linear solver, for example, take more iterations or not scale mathematically, or just take longer in general. And that's driven by the problem we're trying to solve. And sometimes there's only so much you can do with a given piece of hardware if you want to solve a particular physics problem.
So I had, before I take your question, there was someone back here that had a question from yesterday that we had deferred. Can you restate your question again?
Sure. So I had asked, if you had, say, a first-year grad student and they were getting involved in supercomputing, but they didn't really know much yet, what are the sort of skills that would be good to learn? I mean, they have the choice. They could do MPI, OpenMP, CUDA, they could do anything. What's a good thing to invest in?
So pretty much all of our software at some level is built on MPI. I think that's a good base. I actually think that calling MPI directly is not a necessary thing. So there's a lot of libraries that that exist that are built on top of MPI. Unless you need to drill into that level, then it doesn't matter so much. So thinking about algorithms collectively, thinking about how to decompose a problem that you really want to solve into some like abstractions into something that maps onto the library interfaces. I think that's important. I think the mathematics of what you're doing is also really critical. So if you give up convergence in order to do something that, say, parallelizes well, that's not a win. So metrics for comparison that are really relevant to the end scientific or engineering goal, I think that's really important.
So Jed, on the MPI issue, if you had sort of stated if you've got packages that you're using, maybe solver packages, there's meshing libraries or so forth that use MPI. Are you saying you really don't need to know the details of the MPI message passing library in order to use packages that use MPI?
Yeah,
so
exactly.
Okay, so how deep a knowledge do you really need of MPI to use various of packages that we've talked about here? Any at all, really?
So there's plenty of PETSI applications, for example, applications that use PETSI for various things, that use other libraries like libmesh, for example, and they basically never touch MPI. They probably have an MPI communicator, and that's an important concept. For simple applications, you just take ComWorld, and that ends up getting passed around. But the concept of collective operations is important.
Okay.
But the mechanics of setting up your send and receive buffers, of dealing with data types or choosing what MPI function specifically to map to, that's a second order thing. That you don't need to start with that.
Okay.
The description I was going to give of it is not whether you learn MPI, but what are the concepts behind message passing, and what is good message passing paradigms, and what would you like to avoid? Or, for example, neighborhood communications is going to be more effective than constant collectives or whatever. Having the concepts is important, and what's causing, so there's that for message passing. Now, we got away for about 10, 15 years. That's all we had to worry about is that concept. Now, we're back to the old days where we have to worry about vectorization, so concepts of coloring and that. You need to get those concepts down, and then, when it comes time to implement, whether you have to worry about learning CUDA or you're going to use OpenMP or OpenACC or whatever, that some of those decisions are going to change in the next couple of years. Well,
That's
hopefully.
an exercise left for the reader.
Yeah, well, I mean, I don't want to downgrade the fact that it's painful and very time consuming, but if you start there and you worry about that and you don't have the concepts, you're never going to use it well. So focus on the concepts of the methodologies of what's important for parallelization, what are your options.
I know when I was first learning MPI, there was a book out at the time. It was one of the earliest books, and it was the concept of collective versus independent communication was one of the things right at the top of the manual, learning what that meant and understanding what that means in terms of a library, for example.
And I would find a problem that you want to solve and kind of structure things around that. Because just because the machine can do something, it doesn't mean that you want to do that. It may not be in your critical path to solving a problem. So find a problem you want to solve, and there's going to be appropriate technologies for solving that problem. And be very skeptical when somebody says, oh, you should use this funny thing, right? Often it's not really going to benefit you. So look along that path for the kind of problem you're going to solve. Where's your data coming from? What's the intrinsic physical coupling of the system? You can get a lot from intuition about the physics of the problem, the nature of the mathematics that's required, and then find appropriate technologies.
Okay, other questions? Go ahead. Oh, I'm sorry. Brian, I interrupted you again. Go ahead.
Yeah, I would say the first thing to do is decide that you're going to be a good scientific computationalist. And then afterwards, sometimes you'll need a big computer and sometimes you won't. Good scientific computational techniques will be translatable. So get good at your workflows, learn your visualization technologies, know how to do data warehousing and data archiving, know how to at least log on to the centers, how to use a batch system. You know, there's all this kind of stuff that's around the programming model. And yes, the machine and the programming model will be flipping around a bit, but these other things are fairly slow-moving targets, and your skills will be quite translatable. So yeah, debugging, learn parallel debugging, learn about visualization techniques, know how to write your PDEs, know what discretizations do and how they work. Numerical methods are probably more important than your computing.
You had a question?
Yeah, I have a couple of questions, probably open-ended, but I get an impression so we're trying to say that by hexascale we'll just throw more processors, more cores at it. But there are problems in physics which are becoming more and more of interest, which are multiphysics. Sometimes they use explicit methods, and you cannot really just throw more cores, but you have to simulate things longer. So my question is, so where is this exascale initiative on that? Because I get a feeling like we're like the Mira systems are for like 24-hour simulation. Is that enough for solving the most challenging multiphysics problems? Just with throwing having 8,000 cores for 24 hours, is that enough? Or should we also think about running simulations longer? Because there is a scalability issue. Not every algorithm is going to scale up. These are codes that have been developed for over a decade.
So the question basically is, for those class of problems to be solved where multiphysics maybe need explicit methods that obviously don't scale too well, is the fact that it just needs to run for a really long time an acceptable computational paradigm?
It's hard to get allocations that way. If you have a lot of physics that needs to run for a long time, then you really have to go back and really make an argument that this physics can't be done in parallel, right? If you really can make a case that this float has to follow this float, has to follow this float, if you actually can make that argument, then it's hard to argue with you. You can put that right in the proposal and say, this is a extremely long sequential calculation which has no ability to have parallel acceleration.
But limited ability, not
It's just, limited.
limited in the sense that you could probably get a 50% boost in rate or something, but after a point it just flattens out. You would not get I'm sure there are several examples that you guys could think of.
So I have an anecdotal bit of information for that. So many times the codes that we run at Livermore for some of our flagship simulations will run for maybe 15, 20, 30 days to get the results out that they want. That was true back in 96 and 97 with Blue Pacific, the first major IBM system we put in. And I did an interesting calculation where one of the things that Livermore does is simulate nuclear weapons. So at that time, the Blue Pacific was a 2 megawatt system. That's how much power it consumed. So if you ran a weapon simulation on it for 30 days, the amount of energy you would consume was about 3 kilotons, which is just kind of interesting. I was going to ask a question. Typically, for your packages or simulations, how long do they typically run? Do they run for hours, days, weeks, and how many cores? What's typical run sizes?
We vary. So some people run at the hundreds of cores, so 200 to 800 cores, maybe 1,000 cores, but you want a day. You need to be running for about a day. Some people run on all of Edison, so you're at 140,000 cores. And again, any runs less than a day don't tend to generate much useful results. I'm kind of only ticking forward so fast. I think most of our codes are in that category. A simulation campaign might take a couple weeks, and maybe you only get 2 or 3 simulations in that few weeks, so you better you better know your statistics. You better know what kind of ensemble that generates. Other times that 2 or 3 weeks is a few hundred simulations. But 2 or 3 weeks is a typical simulation campaign time. And if you, depending on how many simulations you run, if each one is like a serial job, but you're going to run 10,000 of them, you might get more science that way. So kind of running it embarrassingly parallel might be the only way you get your time through the machine to do your science on the back end. So I've seen small kind of ODE integrations where they're changing the parameters they look at. And doing that kind of model, you can use a lot of compute power and do good science, even if the actual kernel itself doesn't scale very well.
So when you say it takes a long time to run, what does it do to?
It's let's say you're trying to simulate systems at molecular scale, nanoscale. The time step is small; it's femtosecond, and there's no way you can get away from it because that's and it's explicit methods for integration. And then on top of it, if you're considering additional aspects like molecular charges and things like that, there's literally no way you can get away with it. And it's not a good strategy to generate too many restarts or have a lot of restart files. So in that scenario, it's probably better to just take like a 200 cores or something or 100 cores and just run it for a month.
Well, maybe. But another alternative is this parallel time integration that I was telling you about. Yeah. So Jed shaking his head, but it's a hard problem, but
Femtosecond modeling is strongly nonlinear. So parallel time
yeah.
is very hard to get right.
Well, hard is one thing, and impossible is a different thing. So
Can you elaborate just for a moment on parallel on time methods, Rob?
just think of it as an extra dimension that so you solve the space-time problem in parallel instead of just treating it as a special direction where you time march. We're just so accustomed to doing the time marching thing. It's just a new idea. Well, it's not a new idea. It's actually like 50 years old. But we've done very little research on how to solve those problems because the algorithms that you would use to solve the space-time system in parallel would be some sort of iterative method. So they'd have to converge. So you have all the questions about convergence that have to be dealt with. So it is a hard problem, especially in general. If you look over the broad, applications that we have and the different approaches we have to doing time stepping and all these kinds of things. But it's still a possible answer to your question. And we've shown you can make it work and people have shown that you can make it work in certain scenarios. They're the simple problems for now. You have to start somewhere, but anyway.
So my comment there, many of these applications where we are limited by needing to take a very large number of time steps, we're actually stepping near the stability limit. And these parallel time methods require for convergence to beat, so the number of iterations to be significantly less than the number of steps in time. You end up needing some acceleration from a coarse integrator. So that means you need some stable thing that can take a longer time step. That's why I'm not very excited for this kind of application in parallel time methods. As far as these kind of applications, I would say this is really common also within DOE. I would say there's institutional pressures to find things that it can run wider instead of just run longer. Unfortunately, sometimes that compromises science, sometimes it causes creative new solutions. So a very important factor is ergodicity. So this is the property that ensemble averages can give you the same kind of information as longer time averages. So some physical systems have enough of that property and some don't. So if you don't, then you generally have to run for longer. I think there's also a big important question of, is that long-running simulation, is that computing something that's well posed? Or are the questions that we're asking, in fact, not well posed? And we're just getting anecdotes from individual simulations that maybe we can't make good predictions with.
So I saw several hands go up, so
Okay,
you first.
I'd like to follow up.
Okay, go ahead, Mark.
I'll try to make sure I do this reasonably quickly. But it's going to be an answer in a rather different direction. As computers really came online and started invading everybody's lives, you always heard these stories. Well, gee, if cars only advanced as fast as computers, we'd get 1,000 miles to the gallon and a car would cost $1.50. But the problem is, with computers, they were so far from reaching the limits of what they could do with the physics underneath them that they could keep advancing. Where with the car, we've been a lot closer to that. With the aerospace industry, they get 0.5% improvement on lift. They go nuts. The champagne's flowing. Well, you can imagine if we only got 0.5% improvement in the next generation computer, what we'd be doing, right? Some point, it'll probably get to the situation we're running out of luck. Light only moves so fast. We can only push things with so much energy, etc. When that's going to happen is we're a lot closer to that than we were 10 years ago. So there is going to be that issue, and that is going to come up probably in your careers.
Okay, so take your question, and please be ready to ask yours as well. Go ahead.
So suppose for somebody who's relatively new to this high performance computing, let's say for message passing into, let's say for MPI, there are many different commands which can do the same purpose. Let's say you can use either non-blocking send receive, you can use buffer send receive, or let's say send receive if two processes are going to communicate. How do you decide which is the best strategy to use for communication?
So how do you decide which of the various calls in the MPI library at different points in your algorithm?
Well, so the first part of the answer to that is when I made the comment, understand what message passing is and what it can do. Couple that with Jed's comment of making sure you understand what your application needs and doesn't. That's going to tell you what you can get away with. In other words, if you know what costs in message passing, what's efficient in message passing, and why, you'll know what you'd prefer to use. Then you look at your application and say, can I get away? How much of that can I get away with, and when do I have to do something else more expensive? But somebody else the others here can answer this in more technical detail.
So I would never use ready send. So ready send, usually you can't have the information to know that they're ready unless there's some other inefficiency in your algorithm. So just don't deal with that, and you don't need to think about it. Also, buffered send, usually you never need to touch that. Also, normal send and receive, usually you're sending and receiving from multiple places, and so you don't actually want to block on that because it sequentializes things more. And so if you're doing send and receive, it's usually I send and I receive. And I think they could delete all the others from the standard, and it wouldn't make a big deal. Neighborhood collectives are actually different. You can do different things with them. One-sided is actually different, although often what you need for a rendezvous with one-sided ends up adding up to the same kind of stuff. But on some hardware, in some kinds of algorithms, one-sided makes sense. When possible, collectives are usually good. And especially if you have pretty irregular communication, you have things where there's, like if you're solving graph problems, sometimes you have lots and lots of neighbors in some directions, and doing that all over point to point is not very good. That said, I actually don't think these questions are terribly interesting. It's a low-level implementation thing that some of it is making up for deficiencies in the MPI stacks that are provided by the vendors. So, for example, there's times when sticking a barrier in front of a reduction makes the reduction faster. Well, that's stupid, right? If it's faster to do a barrier before the reduction, then the library should do the barrier before the reduction if that helps on the wires. We shouldn't be putting that in our application code. So working around these kind of poor implementations, that's a hassle. It's kind of a failure of the either the community or the vendors or whatever, and we should push back on that because these aren't interesting problems. This doesn't get our science, it doesn't advance things that are important, just working around, issues.
Yeah. Jumbo is built completely upon I send, I receive, reduce, broadcast. That's it. Those 5 functions, and there's one area where I do comma splitting, but the user doesn't see that when I'm building my meshes in parallel. But otherwise,
What about MPI and NIT?
I have NIT and finalize. It's hello world plus I send, I receive, the various weights. And if you're good at those, so you're not going to lock. Deadlock is a big issue with message passing, and the amount of time you waste debugging deadlocks is nuts. And a well-written I send, I receive, wait, messaging process is pretty robust, and it'll work everywhere. So trying to overlap computation with that, maybe only in the last machine or two I've seen any overlap work. The CPU tended to be involved in the I send, I receive, but it's still a robust implementation. So.
Okay, question.
One small question.
Go ahead.
If you can please give us some reference to like parallel time integrity, like splitting our time steps also in
yeah, we have a website you can visit. If you go to the Hyper website, on the side, there's a link that points to the parallel time work we're doing at the lab. And there's more information there. Papers, there's a code that we have that's public release right now. It's pretty new stuff. We've only been working on it for a couple years now, 3 years maybe.
If you're having trouble finding it, you can go to the training examples from last night and click through, and there's links to the Hyper website from there. So, okay, so let's do this at the back there. Go ahead.
I was going to get back a bit to the previous question, because regarding the wide and narrow problems or the scalability of problems, and what I see is the problem of the community and of the procurement is this Linpack metric is making the machines wider and bigger and beefier, but it's not necessarily good for many problems. So what is your view on this, and what is your view on pushing back and pushing the centers to actually buy clusters of tightly coupled, very fast tightly coupled chunks of machines with loose coupling in between them? Because it's much cheaper to make such a machine, and it could actually be feasible to make small blue jeans, many of them, instead of make a ginormous.
So this is capacity computing, right? So capacity computing is I have a lot of compute resources that are not really integrated all that well, but I get a lot of science throughput.
No. What I mean is make a compact version of the blue gene and stick 8 of them in a compute center.
To some extent, we do that. I mean, not necessarily with the Blue Gene architecture, but we certainly do that with standard, off-the-shelf Linux systems, and we call that capacity computing.
And does it have a Blue Gene class network?
Do we do that very often with that kind of architecture? And why Blue Gene specifically? Are you interested in doing it with that specific architecture?
Because I'm talking about a specialized, very fast network, but only in a segment of a machine. So not try to span it across a very large machine, because that becomes very expensive. However, for many problems, tight coupling of a part of a machine with a very, very fast network would be very helpful.
So there's an institutional challenge of how machines are bought and how machines are justified. And so currently, one of the arguments for why we need to have a small number of leadership class facilities is that we have these very large, tightly coupled applications that need to be able to run on the whole machine. And if you remove that, then how do you justify only having a couple leadership class machines instead of, say 50 machines that are all much smaller at many different centers, right? So that's not actually necessarily good for users, because now they have lots and lots of different machines that they could possibly get an allocation on, and which ones should they use, kind of a little more fragmented. So you can take an argument from economies of scale, say, yeah, most of our jobs are these medium scale things, but if you have important things that need to run on the full machine with a fast network, then that's justification for building a very large machine. Now, I think there's misrepresentation of what most of those jobs on that kind of machine are. But if you have to run those, certain capability class, then you have to build that machine once, right? And now you have this global network that's hopefully good, and it may not be best for most of your applications.
So I want to interrupt. We have about 5 minutes left, and I saw several hands go up, so I want to limit us to a minute now. And would you mind if we moved on to other questions real quick?
I want to address the Olympic issue.
Oh, okay. Sure. Go ahead.
So we are building other benchmarks. So I'm involved in the HPGMG benchmark, which is the high performance geometric multigrid benchmark, and we're putting it to the vendors and putting it on the new machines and coming up with rankings. And at SC we have a BOF where we invite up the people who have run the benchmark and what their performance numbers are, and there's a metric that comes out of that. And yes, it ranks machines differently than HPL does. It has some favor to the network, it has some favor to the interconnect, it's more balanced. But it's an uphill battle, right? HPL has a long lead time and a lot of history. So we're working on it. So we'll get adoption if we can.
Oh, just a quick thing. The recent Coral procurement and the procurement that led to Cori had nothing about HPL in it. They had real applications, how they run on today's machines, and a factor faster, hopefully, on the Coral or Cori machines. No HPL.
However, many of those benchmarks were in very unrealistic configurations, not actually representative of the applications sitting behind. And from what I hear, vendors came back and said, we could install Ethernet and it would do fine on almost everything in this benchmark. We know that you don't want Ethernet, and so we'll actually deliver a good network. But I would say that benchmark suite with things like Neckbone, which is basically DGEM as a proxy for actual NEC, which spends half of its time in the coarse grid solve, which is all network latency limited. These things are not
real applications also, not just the Neckbone, and applications that traditionally have run a lot of cycles on our machines, so they're relevant. Could we do better? You bet.
Okay, so question here, yes?
Yeah, what is the importance of fault tolerance in these processes which run on thousands and millions of cores?
Importance of fault tolerance on these very large systems.
Well, so I just don't think it's that interesting of a problem. So the vendors, when you ask them on this, they say people are buying machines that have this given reliability. We engineer for that reliability. So every center in the world, they could buy consumer-grade hardware. They don't. They buy server-grade hardware. Well, why? There's a premium involved, right? Especially for the GPUs. There's a premium involved, and they want that improved reliability. So fine. Yeah, like everybody is putting the money up saying, we want this reliability. The vendors say, we're going to keep delivering that reliability. And some people get really worried about, the machine's going to crash all the time. Well, we've always been at this point where, for like the history of computing, sometimes you have failures, but you mostly checkpoint restart done in a smart way is a reasonable thing to do. Now, often people have I/O bottlenecks, and that's a problem they should fix. Then we have technology like burst buffers, which should help with our checkpoint restarts.
Do any of our panelists care about fault tolerance? Sorry, my minute's up. So who finds fault tolerance interesting? Anyone? Okay. Question, go ahead, Mark.
I won't be so
From the perspective of people that develop numerical algorithms, it's often not hard for us to start thinking about what we would do if there was a fault. The biggest problem we have in dealing with this is who's going to tell us about the subtle faults as opposed to, something just crashed or whatever. And then we talk to the hardware people about it, and they start snickering at us and saying, we're going to have to take care of that. You can't possibly do it.
What's an example of a subtle fault?
Latching error. Like a latching error, data moving from a register back into L1, flips bits.
Okay, all right.
Right? And you can't see that,
Okay.
and so that's a soft error. If it happens too much, they won't be able to sell the chip, right? We're not the only consumer here. In fact, we're the tail, not the dog. So we buy chips that are being put into all these products. So, really the reliability of your devices is set by the contemporary operating systems. So the rate at which your iPhone crashes is about the rate that a node is going to go down. So that's higher than
Jeez,
you
I
expect.
hope not.
But yeah,
My Android.
you are seeing more unreliable hardware.
We have time for, it's right at 10:30. You mind if we do one more question, Paul?
Right, and then I have an announcement.
Okay. All right. So last question back there. Go ahead.
So I'm going to play devil's advocate here. So 2 weeks ago, I had a conversation with someone, and he has a viewpoint that I strongly disagree with, but I would like to hear how you guys take on this viewpoint. So this individual has said, exascale computing has not done anything new. Basically, what we're doing in exascale computing is that we are solving problems, everyday, real important problems that are important to our very lives, but the fundamental science behind these simulations is based on physical laws that have existed for the last 100 years. So I'm sure there are examples out there that without 100,000 cores, without 200,000 cores, that such scientific problems would not have been achievable. So I guess my question to you guys is, what are these examples?
I would say that in every area where I do modeling, we have had to make compromises in the model in order to actually run in a reasonable time. And with a larger compute resources, and I have some idea of what the ordering of these terms are. And I know that if I could put things back into the model, so I take the old BBGKY hierarchy from kinetics all the way down to, say, fluid models. And in between, so for plasma physics, there's a lot of terms in there, so sometimes I use MHD. MHD is still not correct. That's not what a plasma is doing. But MHD is the only thing I can run in my lifetime in the core and get an answer in for multi-second simulation. I would probably add more terms to MHD, extended MHD. I would probably add, with all of these things, make it slower. I need more compute power. So fusion, certainly. Climate, certainly. Subsurface, you have similar problems. My equations of state, my biology I want to add, all the other things, I can't add them now because I won't finish in time. I won't get an allocation that's big enough.
So that's a great question. I'd actually like to hear answers from all our panelists, but we're gonna let Paul comment. We're gonna have to bring the panel to a close. Let's follow up with that question with our speakers individually at the break, if you'd like. And let's. Can we let Paul comment? Sure. Okay.
Well, I'll just have a couple of quick comments. One is the project that took us to the moon didn't use any new physics. It basically used Newtonian physics, right? But in terms of applications that have been run the last few years, some in materials modeling that required all of Mira for several weeks, but staggered over time because we can't give one application the whole machine for weeks. Were they using new chemistry and materials models? Not so much. But they had enough science, not everything the model wasn't as complete as you would like, but they had enough. And by somewhat of a brute force, were able to explain some phenomena that people care about in why corrosion cracking happens in nuclear reactors, for example, and a way to ameliorate it. So, that's one example. Another was simulation of the summer and fall of 2005, 10 years ago, the Katrina summer, simulating the the hurricanes in the Gulf of Mexico, and by having very fine resolution and pretty long run times, a team at University of Colorado Boulder was able to do a very good representation of what happened that summer. That there were more Force 5 hurricanes than any other known season, that there were later ones in the year. One didn't end until beginning of 2006. So again, was that the best weather modeling? I don't know about that, but it was a big dramatic difference from what you could do with, say, a 25-kilometer resolution. And so that's something that it would be impractical to do on smaller machines just because it would take so long. This was done over a period of just a few months. So You want to close the panel?
Yeah, let's thank our panelists.